So let's take a look at a one-way ANOVA. Keep in mind that despite the fancy name, ANOVA is really just looking at several groups and seeing if there's a difference between the averages of any of the groups. So the null hypothesis is there's no difference in the average of any of the groups, and rejecting that would mean there is some difference, at least one difference somewhere in there. So we're going to take a look here at a research article. ANOVAs get reported in many different ways. This is a common way that they get reported. This particular article looked at body image, contraceptive use, sexual health, and specifically what they wanted to add to the research literature is they were going beyond just white women. So a lot of previous research had done a similar thing, but only looked at white women. So they they included women from a group of different races and ethnicities. So let me just jump straight to the part where they did an ANOVA. One of the things they were looking at was the body size based on the body mass index. And here's what an ANOVA looks like when it's reported, or here's one way that it can look at. So they split it into these different, you can see these different groups. This would be the Asian women, white women, Latina, Black, and multiracial. And each of them is followed by M equals something. Sometimes they'll also put a standard deviation in there or something, but they should give you the means. And sometimes they'll give a visual. I personally like it when they give a graphic, but a lot of times they don't. So what is this telling us? It's telling us that the Asian women in this report, of all the body mass indexes that they reported, the average was 23.65. Of all the whites, the average was 25.63, and so on. So we have the averages of the 5 groups. Looking at that alone, we can't necessarily say whether there's a significant difference. Keep in mind, when we say significant difference, we're saying, do we expect that there would be a difference in the population? Or could it just be that the Asian women in this study happened to have very low body mass indices just by pure randomness, and the Black women in the studies, for example, had higher body mass indexes? So a statistically significant difference here would tell us that no, it's not just these little differences. I mean, in the sample, there clearly are 5 different averages. That's definite. That's certain. At least reported averages. What we can't tell by looking at these is whether or not there's significant differences in the population. Do we have enough evidence to believe that there are actual differences by race in BMI in the population? And that's where an ANOVA comes in. And an ANOVA tests whether we're just seeing it in the sample or whether we expect it to happen in the population as well. And this is how it's typically reported. This F tells us that we're using an F test, which is the type of test, it's kind of the engine that drives an ANOVA. This number right here is degrees of freedom. You don't need to worry about that too much, but if you want a real quick what it is, this first number is 1 less than the number of groups. So we had 5 groups, 4 would be 1 less. And this is related to the sample size, the number of total women in this case, I think was close to 490. It's not, you might as well just look how many women were actually in the study, but that's where those come from. So this then is our F statistics, similar to a T statistic. Again, don't worry about this too much. This drives the p-value. So this is just used to calculate the p-value. That's where you would want to focus your attention. So again, the null hypothesis, p-value is always attached to a null. The null hypothesis is all 5 averages in the population, the population average BMI for Asian women is the same as the population average for white women is the same as the population, and all 5 are the same, we have pretty good evidence here, below 0.05 certainly, that that's not the case, that there's some differences there. And that's where the overall ANOVA stops. It just says, yeah, we're going to reject the null because we think there's some differences in there somewhere. Or, no, we don't. We're going to fail to reject because we don't have enough evidence that there's some differences going on. It's possible that all 5 means are the same. Then we would do post hoc, and that's what they look at here, because that's going to tell you, so we know there's differences. The first question that comes to mind is where are those differences? And you might look at it immediately and say, well, white's the lowest and black is the highest, so that's a clear difference. And that's often the case. The lowest and the highest are often significantly different. But that's not always the case. It can depend on variance also, and plus we don't know right now if white and Latina are significantly different or not. So they ran Bonferroni, which tells us they're correcting for these multiple comparisons, and of all the different comparisons, I think there'd be 15 comparisons there. The only one that was significant was between black and Asian. Sorry, I was saying white was the lowest, Asian there is the lowest, and that was the significance. This M difference just means on average what was the difference that we saw in the BMI of the Asian women here and the black women. And then this tells us that we're pretty sure it's not just our sample. We're pretty sure that if we would go out into the population and look at the actual average BMI for all black women and compare it to the actual average BMI for all Asian women, that the BMI for the black women would be higher. We don't necessarily have that reassurance that the other differences would be seen in the population. We don't have enough evidence here just based on our sample alone. And that's the interpretation of a one-way ANOVA.